Hi, so in the previous episode, we talked about the sigma algebra and the probability measure, right? So in this video, we'll use those concepts to build a definition for the sigma algebra measurable function, and which is just another name for the random variable, okay? And then from this definition, we will know what does it mean for the f measurable or the sigma algebra measurable. Okay. All right. So now let's do that. So suppose a tuple omega and a curly f and p. Okay. To be a probability space. Okay. All right. So in this tuple, the omega is a non-empty set, okay, and this f is just a sigma algebra. Okay, so remember that this a sigma algebra is just a collection of this of a subset of a power set, right? So that's simply the meaning of sigma algebra, right? And that is a collection of subsets satisfying some requirements, right? That's not a difficult concept. So this f is a sigma algebra, and that is of the subsets of omega. Okay, should be the power set of the omega, right? And so this p, the probability measure. Remember, a measure is just a function, right? So a probability measure is a measure satisfying some properties for the probabilities, right? So this p is a map from this f to 0 and 1. Okay, so this is a probability measure on f. Is a prob measure on this f. Okay. All right. So now what we're going to do is to have another function. Okay. So suppose we have a function x, let's say it's a map from omega to real number. Okay, so what we want to do is to measure the probability of x belonging to some subset of r, okay, of real number. Okay, so we want to measure the probability of x belonging to some subset of the real number. Okay, so now the interesting thing, or the most interested part that we want to see is this x, right? So this function, and we want to discuss this some probabilities on this x, right? So so it means that we want to assign the probability to some sets. Okay, that is, okay, we want to assign the probabilities to some sets in some forms. Okay, so it should look like something as follows. Okay, so let's say this x is in some set A. All right. Okay. And normally we define this as x inverse a, okay? And which is just a collection of those omegas from omega, big omega, where this x given omega is in a, okay? And we want to assign the probability to the sets of the form with those sets, okay? And for the Borel sets, okay? So those A's are the Borel sets, okay? All right, so, and you can check the definition for the Borel sets and the Borel sigma algebra from the previous episode, okay? All right, so we wanted to make some sense to this, right? So we need to make sure that this x belonging to A, okay, so this kind of set is in F, okay? All right, so such that so that we can actually study the probabilities on this x, right? As long as it's in the F, in the sigma algebra, is in the sigma algebra, right? So okay, to make sense, we want to make sure that this set with x in A and this set is in this F sigma algebra, okay? And this has to be true for all the A's in the Borel set, okay? All right, so otherwise we cannot actually assign a probability to that, right? Because this probability measure is only defined on this F, right? So otherwise we can't assign a probability to that, right? Since this probability measure P is only defined, okay, on this F, okay? All right. Okay, so if we have those above, as mentioned, okay, so it means that whenever this function or this map x from omega to a real, when this function satisfies that this x inverse A is in F, okay, for all the A in the Borel set, then we say that this x is F measurable. Okay, so that's the meaning of F measurable. So that's just measurable towards some sigma algebra, right? So whenever this x satisfies this for all the A's, okay, and we can say that x is F and Borel measurable. And normally we can omit this Borel set here, right? So then we can just call this as F measurable, or just F measurable, okay? All right, so, okay, so for a random variable x, okay, right? So for a random variable x, So it makes sense to assign the probability to any set of the form that with the set where there's x in A, right? So it makes sense to assign probability to any with the form x in A that we mentioned before. Okay. So this defines the distribution of x itself, right? So notationally, so we have this probability of random variable x with value a. So this is simply defined as the probability measure with the input as the with this set with this form, right? X in A. Okay. Then we can actually to study this random variable, right? And again, this A is in the borrow sets as before. Okay. Then from here we can notice that actually the f measurable function is just another name for the random variable, right? Is just a synonym for an f measurable function, right? Okay, so so that's the definition for a sigma algebra measurable function, right? And sometimes this sigma algebra is not the most efficient one, right? So we can actually define another notation to actually make it more efficient, right? For the sigma algebra, right? Okay, so let's say if capital Y is a map from omega to a real is a random variable. Okay. Then we say that sigma y is defined, okay, by this. Okay, so it's just the sigma. This is just the notation for the sigma algebra. Okay, so this is a sigma y inverse A, where A is in a Borel set. Okay. Okay, so what's the meaning of this definition? So basically, that indicates that the smallest sigma algebra containing all sets of the form where this y inverse A, right? Okay, so let's write it down. So the smallest sigma algebra containing all sets of the form of this, right? So that would be the most efficient one, or the smallest sigma algebra, right? Okay, so another way of saying, or another way of characterizing the sigma y is to say that it is the smallest sigma algebra that we can put on omega that makes y measurable, right? So another way of characterizing this sigma y is that it is the smallest okay. All right, so let's just use this, right? Okay, so that is the smallest sigma algebra we can put on this set omega, okay, which makes this y measurable, right? Okay, good. So now we have the formal definitions for the sigma algebra measurable function. Okay, right. So that's basically used for us to study some probability properties of the some random variables, right? So basically, those are the same thing, right? On some set x. Okay. So that's the first definition, and another pretty important part of this episode is that we also discussed the definition for the sigma y measurable, right? So basically that limits or that gives us a more efficient or the smallest sigma algebra containing all sets of the this form, right? Okay, as we mentioned before. Okay.